Hello and welcome to video 2 of 2 for chapter 4. Now, in this video, I'm going to have a conversation with you about the concept of entropy. Now, I am going to warn you that entropy itself is actually a pretty advanced topic. So that said, what I would like to do is to try to give you a sense of what it's about, what it really means, in an effort to try to dispel some of the misconceptions that people have as a consequence of pop science and what have you. So, so that said, what I'd like to do is I would like you to think about some dice. So, if you have one die, and we're going to call this a fair die, which means that um, it's not weighted or anything funny like that. It's going to have six sides. So maybe two, maybe three, like that. 4, 5, 6 is labeled. So, if I were to take and I were to roll this die, the chance of me getting any given side is going to be 1 in 6. Now, why is it 1 in 6? Well, if you think of this as having an equal probability of landing on any given side, there are 6 sides. To get one side, your probability of 1/6. So what options do you have here? Well, you have values of 1, values of 2, a value of 3, a value of 4, a value of 5, a value of 6. So if I ask you how likely is it that you get a 3, 1 in 6? How likely is it that you get a 4, 1 in 6? How likely is it that you get a 5, 1 in 6, and so on? But what if I add another die? So, whoops, you don't want to see that. That's yucky, as my daughter says. So here's another die. So my first die has the possibility of getting 1, 2, 3, 4, 5, or 6. And my second die, taken by itself, has the possibility of getting 1, 2, 3, 4, 5, or 6. All equally likely. But when I roll these two dice together and I count the values of their sides, check out what happens. I could get 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12. So if I were to think of these as being identical dice, how many different ways, when I roll these two die, can the sides add up to 2? Well, if I call this die right here die A, and this die right here die B, I have a 1 here and a 1 here. So there's really only one way in which I could get that. What about 3? Well, die A could be a 2 and die B could be a 1. Or die A could be a 1 and die B could be a 2. So there are two possible ways that that could happen. What about a 4? Well, one of them could be a 3. For example, die A could be a 3 and die B could be a 1. Die A could be a 1 and die B could be a 3. Or they could both be 2s. So 3 ways. What about a 5? Let me clear some of these away so I have some place to write. What about a 5? Well, let's see here. I could have die A be a 3 and die B be a 2. A could be a 2 and B could be a 3. A could be a 4, B could be a 1. Or A could be a 1 and B could be a 4. Whoops. So 4. What about a 6? Well, with the 6, you get both being 3s. You get one being a 4 and one being a 2. You get the other one being a 2 and the other one being a 4. You could get a 5 and a 1, or a 1 and a 5. 1, 2, 3, 4, 5. 5 different ways. Whoops. I'll redraw that. All right. What about a 7? All right. Well, a 7, 6 and a 1 and a 6. A 5 and a 2 and a 5. A 3 and a 4 and a 3. And that's about it. 1, 2, 3, 4, 5, 6. 6 different ways. What about an 8? An 8, well, that's a little more complicated. I could get a 6 and a 2, a 2 and a 6. I could get a 5 and a 3, a 3 and a 5. Or they could be both 4. 1, 2, 3, 4, 5. Okay. What about a 9? 6, 3, 3, 6, 5, 4, 4, and a 5. 4. Well, that's interesting. One way to get this, 2 ways to get this, 3 ways to get this, 4 ways to get this, 5 different ways to get this, 6 different ways to get this, 5, 4. I'm going to go out on a limb and say 3, 2, and 1. And were you to actually try that, that's exactly what you would get. So, what's the whole point of this conversation about dice? Well, the first thing I'd like to point out is that the mere act of adding in this extra die goes from taking each number that you can get as being equally likely and now actually gives you a number that is the most likely. So, what do I mean by that? Well, look, when I roll these 2 dice, of which you have, 6 sides here, 6 sides here, 12 different options, if you want to think of it like that. These are how many times or how often you would expect to see those sides. So, for example, getting a 2 or getting a 12 is very unlikely. Getting a 3 or an 11 is more likely than getting a 2 or a 12. In fact, it's twice as likely. But still, it's pretty unlikely. Here, though, this is the most likely one. Now, if I were to plot this right here on what's called a histogram or a frequency plot, let's see, number of ways, and then the number. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. We'll say 2, 4, 6. It would look something like this. And that is a bell curve. When you have bell curves, that means that you have random behavior. That means that you have unweighted dice. And it turns out that when you look at the properties of large numbers of particles, the property of an individual particle is much like rolling one of these dice. So, for example, if you were to ask what the state of the system is, really what you're asking is when I roll all of these dice, what is the most likely number I'm going to get? For example, when you take a thermometer and you measure the temperature of water, you're getting an average, the most likely temperature. I mean, there are places inside that pot of water that are hotter than that. There are places that are cooler, but the most likely one is the one that you get. So, one way you can think about this is that this is a manifestation of how much knowledge you have about the system. So, I'd like you to sort of reflect on your youth. Perhaps you played this game when you were very young. It's called telephone game. What you do is you sit around in a circle with a whole bunch of friends, and you have one person start a rumor by whispering something into the person sitting next to them's ear. What they do is to whisper to their friend, and they whisper to their friend, they whisper to their friend. And by the time it gets all the way back around to the original person, what you've discovered is that what you get at the end of the day probably look nothing like what you started off with. You lost information along the way. Now, that in truth, from a statistical standpoint, is what we think of as entropy. Entropy is a measurement of how much information you have. It's a measurement of certainty and uncertainty. If you're interested in reading more about this stuff, you can look out, or you can look at topics about information entropy or information theory. I think it's called Shannon entropy. Let me verify that. Yes. So, if you think of large numbers of particles, there is going to be a most likely state, a most likely configuration of all those particles that's going to give you whatever pressure, volume, temperature, and number of moles that you're looking at. There is a smaller probability that you might get something else, but there is a number, much like here, 7 being the most likely number that you get whenever you take and you roll 2 dice. There is the most likely configuration of your macroscopic variables. So, like I said, that's really what we think of as entropy. Now, that said, entropy from a basic university physics standpoint is defined this way. We use the letter S for entropy. It's dq over T. It's measured in joules per Kelvin. Okay. Now, that said, there is a consequence of rolling these dice, these molecules, if you don't think of it like that, or these atoms. And that consequence is that entropy has a tendency to always increase. In fact, the only time where you really see it not change is when you have a completely reversible process. So, for example, if you were to look on a PV diagram and you had a process that you could take all the way around to some other location, some other stage, and then back to the original exactly the same way. If this was completely reversible, the change in entropy here would be zero. So the way we usually write this is that when you integrate dq over dt, you're doing it around a closed path. The little circle here means closed path. And this would equal to zero. On the other hand, what if it's not completely reversible? And remember, previous conversations that we've had, tell us that unless you're dealing with like 1, 2, or 3 particles, in general, there are no completely reversible processes. So in a situation where you have an irreversible process, the change in entropy is always greater than zero. Okay, so entropy, like I said, is sort of a measurement of how much information that you have available. But the information that we're looking at here is the statistical state of a system. Okay, and by using the equation for entropy here, we can get a sense of the reversibility and the irreversibility of something. So, as a consequence of these definitions, we have a new way to state the second law of thermodynamics. And that is that the entropy of a closed system never decreases. Now, the biggest closed system that we're aware of would be the universe. As best as we can tell, it represents everything that there is. And as a consequence, it is a closed system. So what that means is that the entropy of a universe, or the universe, never decreases. Now, so that said, let me just do a quick, simple example showing you how you would use this. And in this one, what I want to do is I want to look at the change of entropy of 2 kilograms of liquid water that transitions to steam. Now, we're going to have this sit at the vaporization point for water. So what we've been given here is our mass is 2.0 kilograms. Our temperature here is 373 Kelvin. We're dealing with liquid water. It's transitioning to steam. So the liquid or the latent heat rather of vaporization for water is 2,265,000 joules per kilogram. And what I would like to find here is just the change in entropy. And I'm going to use this equation right here to do it. Now, so well, I'm going to integrate both sides. When you integrate the left side from whatever your initial state is to whatever your final state is, you get your change in entropy. This is your delta S. On the right-hand side, dq is literally just L sub v times m. Okay, so this really ends up being L sub v m over t. So here, 2,265,000 joules per kilogram with 2 kilograms divided by 373 Kelvin. So we're going to plug this into my calculator. I get about 12,000 joules per Kelvin. Is positive, as you can see. So the act of taking this thing from a liquid state to a gaseous state causes a positive change in entropy. Okay, which should make sense. That's not a reversible process. Okay. Now that said, I would like to also mention that there is a third law of thermodynamics. Now, the third law of thermodynamics is a consequence in part of quantum mechanics. Okay. So if you think of temperature, as being proportional basically to, the average kinetic energy of the system. I'll just write it as K because that's what we did before. If you think about an actual atom and this is, I want to be very clear, this is the wrong way to think about it, but just for the sake of a macroscopic understanding of what's going on, you have this little electron that flits around the proton on the center. It's the simplest one, it's just like hydrogen. There's no way that you can take away all of the motion that's going on inside here. You can't stop the electron from going around. Even let's pretend you could. The proton itself is made out of 3 quarks. Those quarks are constantly rolling around on the inside, going up to higher energy levels, falling back down, what have you. I guess what I'm trying to say here is that if you're really wanting to get rid of all the kinetic energy, all of the motion inside something, it turns out from a quantum mechanical standpoint, that's not possible. You cannot eliminate all of the energy. You can't eliminate it. It's just not possible. So if you think of temperature as being related to kinetic energy again, and you can't make this zero. This is never exactly zero. What that means is that you never see temperatures of zero. Now remember, this is a consequence of 3/2 K sub BT is equal to 1/2 mv RMS squared. I mean that's the basic equation that we came up with for you know uh, the relationship between temperature and kinetic energy. But if you can't get rid of this right stuff all the way, that means that you never see a temperature that's zero, which means that you never see absolute zeros. Really should say zero absolute. Okay, so zero absolute is not possible. Now, this in itself, you can also think of as being related to the second law of thermodynamics. If you remember in the previous video that we did, I mentioned that you never see heat engines that are 100% efficient. That was one of the statements of the second law. So, if you think about a basic design of a heat engine from an efficiency standpoint, what you're doing is you're looking at the relationship between QC and QH. QH is the reservoir that's holding the hot stuff, and QC is the reservoir holding the cool stuff. Okay. Well, if you think of this, say, from a Carnot cycle standpoint, you could also write this as 1 over, TC over TH, or 1 minus TC over TH, rather. Here's the deal, though. The only way that this could be 1 would be if Tc was 0 or Th was infinity. With Th being infinite doesn't make sense. We're not aware of any situation in nature where you have an infinite temperature. That would imply an infinite amount of energy. What about Tc being equal to 0? Well, here's the deal. The third law of thermodynamics tells us that that's not possible. You never see situations in nature where you have 0 absolute because you can't remove all of the motion. You can't remove all of it, which means that this is never, ever, ever equal to 0, which means that your efficiency is never equal to 1. So it's not possible to have a 100% efficient heat engine. And in truth, it's not possible having a 100% efficient process in nature. Okay. So, like I said, it's easy to see how these laws are misunderstood. People get very weird about, the second law of thermodynamics. And a lot of it has to do with the fact that they don't understand that entropy itself really is just a measurement of how much information you have. It's like playing the telephone game. There's so much going on inside your object that makes it impossible for you to know all of what's going on. So there's a lack of information, which means that your entropy is maximized. All right, so that's it for this video. And I will see you in the next chapter, which is going to lead us into talking about electricity and magnetism. And I'll see you then.